Okay, this is example 67 in section 4.5, applied optimization. And we will first read the problem. You have been asked to design a 1-liter can shaped like a right circular cylinder. So just imagine a soda pop can or something like that. That's what it means by a right circular cylinder. It has a base which is a circle, and then it goes straight up everywhere, so just like a can. The radius of the circle at the bottom of the can is r, and the height is h. We're going to call them that. And what dimensions will use the least material? So what value for r and what value for h will use the least material to construct this can, knowing that we want the can to contain 1,000 cubic centimeters or 1 liter. So the amount of material that you're going to need is a surface area. So what is the surface area of such a thing? Well, it has a top and a bottom, which are both circles. So the area of any circle is pi r squared. So we have two of those guys. So that's 2 pi r squared. That's the top and the bottom. And then the surface area of the side is, imagine if you were to cut it and fold it straight out, it's just a square, right? If you take the side and you cut it straight down and then lie it and fold it straight out on a table, it's really just a square, where the base of that square is the circumference of the circle, right? When you cut it and fold it out, the base of the square would be the circumference of the circle, which makes up the bottom and the top. So the circumference is 2 pi r. That would be the base of the square, and then the height would be h. So that would be the side of the cylinder, 2 pi r h. So we have this this total surface area. Now notice that it's in the form of, it's a function of two unknown variables, r and h. So what we would like to do, because we're in Calc 1, we're not working with functions of more than one variable, is be able to figure out what r is in terms of h, or h is in terms of r, and plug it back into here so we only have a function of one variable. So how do we do that? Well, we know that we want the volume to be exactly 1,000 cubic centimeters. And what's the volume of such a guy? Well, it's the area of the base, which is pi r squared, times the height. That's how much this can hold, pi r squared h. So we want pi r squared h, the volume, to be 1,000. So solving for h in terms of r squared, we get h is equal to 1,000 over pi r squared. So we plug that back in for h right up into here, and you can see the surface area then is 2 pi r squared plus 2 pi r h, but we found h is 1,000 over pi r squared. Simplifying that, 2 pi r squared plus 2,000 over r. Now r itself is in 0 to infinity, because you have to think about, well, what's the smallest r could be? I could push it all the way down to 0, but I can't quite get to 0, because if I got to 0, I'd have no surface area. Right, so pretty close to 0, which would make h get really, really huge. Or we could push r out to infinity, which would make h get really, really, really small. So we cannot include those endpoints. So here we have a situation where we do not include the endpoints. All right. So when we check the endpoints of an open interval, what we're really doing is checking the limits. But it's still the same idea, checking the endpoints. So the bottom line is I first need to find critical points. So I take the derivative, set it equal to 0, I solve for r, and I get the cube root of 500 over pi. Checking the endpoints and the critical point then. Now checking the two endpoints, intuitively we should understand that that should drive the amount of material we're using for the can out to infinity as well. But the limit as r goes to 0 from the right of 2 pi r squared, this piece becomes 0, but 2,000 over a tiny, 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 tiny positive number, that gets closer and closer to infinity, so that drives it to infinity. Same at the other endpoint, the limit as r goes to infinity. 2,000 over r goes to 0 as r gets huge, but this piece goes to infinity. So they both drive the amount of material we're using in the can to infinity. Intuitively, we would know that that's not correct for the answer anyway, so it's going to occur at one critical point that's between 0 and infinity. So S, the surface area at r is equal to the cube root of 1,000 over pi. Work it out. Comes out to be this number, which is the exact number, but if you plug it into your calculator, you get about 553.58 cubic centimeters. Okay, so that's the square centimeters. That's the surface area of the can. So the maximum amount of material that you would need to use is, that should say minimum. Yeah, it does. Minimum amount of material that you would need to use is 553.58 square centimeters, or this exact value, where r is the cube root of 500 over pi, which is about 5.542 centimeters, and h is 1,000 over pi r squared, so the cube root of 500 over pi squared put that in your calculator. It comes out to be about 10.84 centimeters.